Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us discuss some of the applications of rank of a matrix. This is today's class map. In this class, let us quickly recap the concepts of null space, column space, and row space of a matrix, and quickly recap the definition of rank of a matrix, and rank theorem. And we solve some of the problems on related to rank theorem, and we extend matrix inversion theorem using the concepts which we have learned in these topics. This is our class map of today's video. Let us first recall the definition of the null space. The null space of an m by n matrix A, written as null A, is the set of all solutions of the homogeneous equation Ax is equal to O. So null space A will give us the solution set of the homogeneous equation Ax is equal to O, where the given homogeneous system is converted into a matrix form. We will get this form Ax is equal to O, where A is the coefficient matrix. Then null A will give us the solution set for the given homogeneous equations. And we can write null space A as the set of all x such that x belongs to Rn and Ax is equal to O. So the set of all x belongs to Rn and the x which satisfy Ax is equal to O will be in the set of null space A. And null space A is the set of all x belongs to Rn that are mapped into the zero vector of Rn. And we have already seen that null space of an m by n matrix A is a subspace of Rn. So these are the things which we need to remind about null space of a matrix A. And column space of a matrix is nothing but the linear combination of all of its columns. So the column space of m by n matrix A is the set of all linear combination of the columns of A. It is denoted by column space A, COLA. We write it as like this. We pronounce it as column space A. If A is equal to matrix of A1, A2 and so on An, where these A1, A2, An are the columns of matrix A, then column space A is the spanning set of these column vectors A1, A2 and so on An. We have already seen that column space A is a subspace of Rm. Here there will be n vectors. There are n columns, but each column has m entries since the number of rows in A is m. So each column vector has m entries. So it is a subspace of Rm. Since it is spanned by some of the vectors of the vector space, every spanning set of some vectors of vector space is a subspace. That is why null space A and column space A both are subspaces. And row space, the linear combination of all the rows is called the row space. So if A is an m by n matrix, each row of A has n entries and thus can be identified with a vector in Rn. And the set of linear combination of the rows or row vectors is called the row space of A, and it is denoted by row A. Each row has n entries, and row space A is spanned by the rows, and any spanning set of vectors of Rn, a vector space, is a subspace of Rn. So row space A is a subspace of Rn. Since the rows of A are identified with the columns of A transpose, we could also write column space A transpose in place of row space A. In A transpose, the columns of A will become rows of A transpose, and the rows of A will become columns of A transpose. So both are same. Rows of A are nothing but columns of A transpose. So both are same. And we have seen this result about the row space. If two matrices A and B are row equivalent, then their row spaces are the same. If B is in echelon form, the non-zero rows of B form a basis for the row space A as well as for that of B. So when a matrix A is reduced into echelon form and B is its equivalent, row equivalent echelon form of A, the non-zero rows of B form a basis for the row space of B as well as row space of A. And rank of A is nothing but the dimension of column space A. That is the definition of rank of A, and it is denoted by rank A. So rank A is equal to dimension of column space A. Since row space A is same as column space A transpose, the dimension of the row space of A is the rank of A transpose. So rank of A transpose and rank and dimension of column space A transpose and dimension of row space A are all same. The dimension of null space of A is called the nullity of A. And this is the rank theorem. Rank theorem states that the dimension of the column space and row space of an m by n matrix are equal. This common dimension, the rank of A, also equals the number of pivot positions in A and satisfies the equation rank of A plus dimension of null A is equal to n. So with this theorem, with this statement, we can find rank A and dimension of null A, dimension of column space A, dimension of row space A, and dimension of row space A transpose, dimension of column space of A transpose. All these things, if the order of the matrix is given, then we can find the n, and any one, and if we convert that into echelon form, we can find the pivots. We can find the pivot positions as well as pivot columns. Once we know the number of pivot columns, that will be the rank of A, and all other things except dimension of null A. Dimension of null A can be obtained by using this formula. So if a matrix is converted into echelon form, then we can find all these things very easily. So let us do some of the problems related to rank theorem, and this is the first one. The matrix A is row equivalent to B. Without calculations, list rank A and dimension of null A, then find basis for column space A, row space A, and null space. So here A and B are given, and it is stated that B is row equivalent form of A. So here we can observe that both A and B are 3 by 4 matrices, and B is in echelon form. So here this 1 and -2 are in the pivot positions. So these two, first and second columns of matrix B are pivot columns. So given that A is row equivalent to B, and you can observe that A and B are 3 by 4 matrices, and B is in echelon form, and 1, 2 are pivot columns of B. So 1, 2 are the pivot columns of A also, since A is row equivalent to B. Once we find the pivots in pivot columns in echelon form, since we are performing only elementary row operations and both the matrices are row equivalent, we can say that the same columns, the same number of same columns will also be pivot columns in matrix A. So here the first two columns of B are pivot columns. So first two columns of A also pivot columns of A. So there are only two pivot columns. So we can say that dimension of column space A is equal to 2. We know that pivot columns form a basis for column space A. So in column space A, in the basis of column space A, there will be only two vectors. So dimension of column space A is 2. We know from the definition of rank A is nothing but dimension of column space A. Therefore, rank A is equal to 2. So here, without any calculations, we can directly say that rank A is equal to 2 just by observing B, which is an echelon form of A. So simply while saying B, we can say that these two are the first and second columns are the pivot columns, and these two are the pivot positions. So these two are the pivot columns. There are only two pivot columns in B. Resultantly, there will be only two pivot columns in A. So the number of pivot columns is equal to rank A. Once we know the rank A, we can also tell the dimension of null space A. Since we have 4 columns, n is 4 for this matrix A. So since rank A is 2, dimension of null space A is 4 minus 2, that is 2. So without any calculations, we can also tell the value, tell the number or value of dimension of null space A also. So this is what we discussed. From the rank theorem, we know that rank A plus dimension of null A is n. So rank A is 2 plus dimension of null A is equal to 4. N is 4 here since A has 4 columns. So dimension of null A is equal to 4 minus 2, that is 2. And now we have to find the basis for column space A and null space A and row space A, of course. Pivot columns of A form a basis for column space A. So these two columns, first and second columns, form a basis for column space A. So therefore, basis for column space A is 1, minus 5, minus 1, 5, and minus 4, 2, minus 6, which are the first two columns of A. Since these first two columns are pivot columns, so this is the basis of column space A. So for column space A, we need not to calculate anything. We just need a echelon form of the given matrix. Similarly, non-zero rows of echelon form of A form a basis for row space A. So this is the echelon form, and here we can observe that first two rows are non-zero rows, and the third row is a zero row, since all the entries are zeros. The row is said to be zero row when all the entries are zeros. So the third row is a zero row, and the first two are non-zero rows. So these two rows can form a basis for row space of B as well as row space of A also. So the basis for row space A is equal to 1, 0, minus 1, 5, and 0, minus 2, 5, minus 6. So we have already discussed that for convenience, sometimes we write this in this form also. Both are same. That is equal to set of 4 tuple 1, 0, minus 1, 5, and 0, minus 2, 5, 6, minus 6. So we can write in any way. So again, we can observe that here there are two vectors in basis of row space A. So dimension of row space A is 2. And dimension of column space is also 2, since there are only two vectors in column space A, which is equal to rank of A, which is the number of pivot columns in the matrix. So we have already seen that dimension of null space is also 2, since 4 minus 2 is 2. But to find basis for null space A, or the vectors in null space A, we need to convert A into reduced echelon form. The given matrix is in the echelon form, so we need to further reduce it into reduced echelon. Here you can observe that in B, all the entries below 1 are zeros. Of course, it's a property of echelon form, and the leading entry is 1. So no need to do anything for the first column. In the second column, the leading entry must be 1. Here it is minus 2, so I can divide it with minus 2. Second row can be divided by minus 2, so that it will become 1. And we need to make the elements above this leading entry zeros, but here it is already 0. So we need not to do anything in this case also. There are no other pivot columns, so we have nothing to do with these entries while reducing echelon form, while reducing it to reduced echelon. So just by multiplying the second row with minus 2, I will get this, which is in echelon form, which is in reduced echelon form. So let us denote it by C. Now C is the reduced echelon form of matrix A. So for finding the vectors in null A, we need to form an augment matrix AO, which is rho equivalent to CO, where O is the null matrix. So that is equal to C is written here, and in the last column, all zeros are added to this C. So now this became augment matrix CO. We need to solve this system. Equivalent equations are here. This one can be written as the first column is related to x1. This is second column is related to x2, and this is x3, and this is x4. So these equations can be converted as x1 minus x3 is equal to, x1 minus x3 plus 5x4 is equal to 0. That is the first equation. And similarly, the second row can be written as x2 minus 5 by 2 x3 plus 3x4 is equal to 0. That is the second one. And there are all zeros in the third row, so it will not be any equation. So the first equation can be written as x1 is equal to x3 minus 5x4, and second equation will become x2 is equal to 5 by 2 x3 minus 3x4. Here we can find x3 and x4 are free variables. So the vector x1, x2, x3, x4 can be written as this. Value of x1 can be written here. So x1 is x3 minus 5x4, x2 is 5 by 2 x3 minus 3x4, and x3 and x4 are free variables. So this x3 is x3 and x4 is also x4. So this expression can be written as x3 can be taken out. So x3 times, here it is 1, and in the second entry it is 5 by 2 times, so it is 5 by 2, and in the third entry it is 1 time, and it is absent in the fourth row. So it is 1, 5 by 2, 1, 0. That is the multiple of x3. Similarly, if x4 is taken out and x4 times minus 5 here in the first row, minus 3 in the second row, 0 absent, x4 is absent in the third row, that's why 0, and 1 in the last row. So minus 5, minus 3, 0, 1. This vector is the multiple of x4. So if I take this one as v1 and this as v2, then this is of the form x3 v1 plus x4 v2, where v1 and v2 are two vectors in R4. So now, since x3 and x4 are free variables, they are any scalar or any real numbers. So the basis for null space A is equal to these two vectors v1 and v2, that is 1, 5 by 2, 1, 0, and minus 5, minus 3, 0, 1. So null space A is the linear combination of these two vectors. So C1 v1 plus C2 v2, where C1 and C2 are any scalars or any real numbers. That will be the set of null A. And here we can observe that there are two vectors in the basis of null space A. So dimension of null space A is 2. Let us move on to one more problem. So if the null space of an 8 by 5 matrix A is 3-dimensional, what is the dimension of the row space of A? So here it is given that A is 8 by 5 matrix. So A has 8 rows and 5 columns. Therefore, n is equal to 5, m by n. So n is the number of columns in the matrix. So that is 5. Further, it is given that the null space is of 3-dimensional. So dimension of null A is 3. And we know that from the rank theorem, rank A plus dimension of null A is n. And further, we know that dimension of row space A, which we want in this problem, is nothing but the rank of A. So dimension of rank row space A is equal to the rank of A. So in this equation, we know the value of dimension of null A, which is given as 3, and we know the value of n. So we can easily find out the value of rank of A. That is 5 minus 3 is 2. So since the rank of A is 2, dimension of row space is also 2. So we can tell many more values from this one. Dimension of column space is also 2. Dimension of column space A transpose is also 2. Dimension of row space of A transpose is also 2. And rank of A transpose is also 2. So with this little information, we can tell the values of all of this. So this is the problem. Let us move on to one more problem. And this is, if the null space of a 5 by 4 matrix A is 2-dimensional, what is the dimension of row space of A? So here, since the A is of 5 by 4 matrix, A has 5 rows and 4 columns. So here n is 4. We know from the rank theorem that rank of A plus dimension of null A is equal to n. In this problem also, the dimension of row space is given as, it is given as 2, of course. And we need to find the dimension of null space A. Sorry, we need to find the dimension of row space A, which is equivalent to rank of A. So similarly, as per our last problem, it is 4 minus 2, that is 2. So dimension of row space A is rank of A, that is 2. So similar problem to the earlier one. Here we need to observe what is n is. We need to be careful on the value of n. And this is one more problem. If A is a 5 by is a 7 by 5 matrix, what is the largest possible rank of A? That is one question. And the next one is, if A is 5 by 7 matrix, what is the largest possible rank? So what will happen if the ranks and if the rows and columns are transposed? So if A is a 7 by 5 matrix, then A has 7 rows and 5 columns. So one column cannot contain more than one pivot. So no column can contain more than one pivot. So there are 5 columns. So at most there will be 5 pivot columns, not more than that. So A cannot have more than 5 pivots. So A can have at most 5 pivots, not more than that. You can have lesser number of pivots. One of the columns of A may not be a pivot column, but we can't exceed that number. So A, at most A can have 5 pivots. So the largest possible rank of A is 5 in the first case. So in the second case, where A is a 5 by 7 matrix, then A has 5 rows and 7 columns. Here there are more number of columns than the rows. But there are only 5 rows. No row can contain 2 pivots. So since there are only 5 rows, A can have at most 5 pivots only, not more than that. So though there are 7 columns, since there are only 5 rows and no row contain more than one pivot, the matrix A cannot have more than 5 pivots. So in this case also, A cannot have more than 5 pivots. So A can have at most 5 pivots. So the largest possible rank of A is again 5 in this case also. And this is one more problem. If A is a 3 by 7 matrix, what is the smallest possible dimension of null space? In this problem, smallest possible dimension of null space A is asked. So since A is a 3 by 7 matrix, A has 3 rows and 7 columns. So one row cannot contain more than one pivot, as we have seen earlier. So A cannot have more than 3 pivots. So at most it can have 3 pivots. So the largest possible rank of A is 3. Though there are 7 columns. So since the largest possible rank is 3, that means that it may be 2 or 1 also. And we know from the rank theorem that rank A plus dimension of null A is n. Here n is 7. N is 7. So the smallest possible dimension of null space A is 7 minus 3. That is 4. That means in the dimension of null space A, there will be at least 4 vectors. We can have more than that also, of course. If one of the row is 0 row, then it is reduced to echelon form. Then A is reduced to echelon form. If one of the row is 0 row, then the dimension of null space A is more than 4. It may be 5 also. If two rows are zeros, then it increases further, of course. So from the last two problems, we can observe that rank A, the largest possible rank A is, we can say that minimum of number of rows, comma, number of columns. So the minimum of number of rows and the number of columns will be the largest possible rank of a matrix. And from that we can find the smallest possible dimension of null space. And this is one more problem. If A is a 7 by 5 matrix, what is the smallest possible dimension of null space A? So largest possible rank is 5 from our previous discussion, and rank A is the largest possible rank A is 5 and n is 5 here, n is also 5 here. So the smallest possible dimension is 0. 0 is also possible. So if the dimension of null A is 0, then there will be only one vector in the null space of K, that is the 0 vector, which is obvious in any case. So except 0, there will be no vector in null A. That is also a possibility. That is what we are saying. Null space may be more than, the dimension of null A is more than 0. That is also possible, but that case where there will be only one 0 vector in the null space A is also possible when a 7 by 5 matrix is. It depends on the entries of the given matrix, of course. So these are the concepts related to some of the problems related to rank theorem. So using these concepts, we can extend the invertible matrix theorem, which we have already seen in our previous classes. Let us quickly go through what we have seen in the earlier classes. So if a matrix is invertible, many statements are equivalent to that one. So these statements are seen in our previous classes. Let us quickly go through it. Let A be a square n by n matrix, then the following statements are equivalent. That is, for given A, the statements are either all true or all false. If one statement holds, all the statements hold true. If one is false, all the statements are false. And those statements are, first one is A is an invertible matrix, and A is row equivalent to n by n identity matrix. So that means whenever A is an invertible matrix, you can reduce A into identity matrix, and vice versa, of course. And once identity matrix is the row equivalent form of A, it has n pivot positions. Since in identity matrix all the columns are pivot columns, and in n by n identity matrix there will be n pivot columns and hence n pivot positions. And then the equation Ax is equal to O, the null matrix, has only the trivial solution. The columns of A form a linearly independent set. The linear transformation A to Ax is 1 to 1. The equation Ax is equal to B has at least one solution for each B in Rn. All these statements are equivalent, and the columns of A span Rn. And the linear transformation from X to Ax maps Rn onto Rn. And there is an n by n matrix C such that Ca is equal to I. There is an n by n matrix D such that AD is equal to I, left inverse and right inverse. And A transpose is also an invertible matrix. So all these statements are equivalent, and we have discussed in detail about these statements in our previous classes. Now we are adding some more equivalent statements to this one by using the rank theorem and concepts of null space A and column space A. So to these statements, we are adding some more concepts, some more statements too. So let A be an n by n matrix. Then the following statements are each equivalent to the statement that A is invertible matrix. The columns of A form a basis for R. So let us discuss in detail once we go through all the statements. Column space A is equal to Rn. So columns form the basis, columns of A form the basis for Rn, and column space A will be the entire set Rn. And dimension of column space A is n, rank of A is n, and dimension of null space A is 0. So these are to be added today. So if the columns of A form a basis of Rn, then when we are saying that it is a basis, then we have two properties: linearly independence, and the columns can span entire set Rn. So whenever columns of the matrix A form a basis for Rn, the columns of A form linearly independent set, and those columns of A can span Rn. So that is the statement. And the equation Ax is equal to B has at least one solution for each B in Rn. So whenever the set can span the entire Rn, that means every vector in B, every vector B in Rn can be written as a linear combination of those columns, and hence those weights are scalars used in the linear combination is the solution. So for each B in Rn, we can have a solution for the system Ax is equal to B. And column space A is Rn. When every vector can be written as a linear combination of other all vectors of the as a linear combination of the columns of A, then column space A can be equal to Rn. Since here the columns of A span Rn, that means it can span entire set Rn. So column space A is nothing but Rn. which can be drawn from this direction. We know that the dimension of Rn is n. So dimension of column space A is also n. That means it has n vectors in its basis. So rank A, from the definition, rank A is nothing but dimension of column space A. So that is also n. When rank A is n, from the rank theorem, which states that rank A plus dimension of null A is n. So since rank A is n, n plus something is equal to n. That means this dimension of null A is 0. Dimension of null A is 0. That means there will be only 0 vector in the null space. That is what we can hear. So only 0 vector is in null A. That means there is only trivial solution. So 0 solution is obvious anywhere. So the homogeneous system of equations Ax is equal to O has no other solution except this 0 solution. So it has only the trivial solution. So rank A is equal to n, and A is n by n matrix, which we have already gone through earlier. From this we can further get this one. Since rank A is n and there are n columns, A has n pivots. All the columns are pivots. So A has n pivots. From this one we can say that rank A is n. And A is row equivalent to n by n matrix, n by n identity matrix. Since there are n pivots and there are only n rows, so we can say that every row contains a pivot. So every row of A contains a pivot and every column of A contains a pivot. So A can be reduced into echelon form and particularly into identity matrix form when it is reduced into reduced echelon form. So we can say that rho E, A is rho equivalent to n by n identity matrix. So whenever it is equivalent to n by n identity matrix, A is invertible. So all these conditions are if and only if and implies and implied by. One statement is hold good, then the next statement is also holds good. And these statements are implies. First statement implies second one and implied by the second statement also. So we can move in any direction. So if any one of the statement is true, then we can have all the remaining results also. So this is a powerful statement. So it has many tools, multi-tool, and very useful as per the circumstances. As per the given circumstances, you can do any one of this statement, which will give you all the results, all the remaining results. So using this, let us go through this problem. Which is beautifully given in the textbook David Seeley. A scientist has found two solutions to a homogeneous system of 40 equations in 42 variables. So he has formed a 42 variable equations and 40 equations. He has 40 equations. The two solutions are not multiples, and all other solutions can be constructed by adding together appropriate multiples of these two solutions. Can the scientist be certain that an associated non-homogeneous system with the same coefficients has a solution? So this is a real life problem. Let us convert this equation, this problem into our known parameters. So here there are 40 equations with 42 variables. So 40 equations can be written in 40 rows with 42 unknowns. So if we convert these 40 equations into a matrix form, we will get a 40 by 42 matrix. So the matrix coefficient matrix A will have 40 rows and 42 columns. So here it is given that, so the order of the matrix will be 40 by 42. It is given that the above system has two linearly independent solutions. So one is not a multiple of other. The two solutions are not multiples. This gives us the clue that the two solutions are linearly independent. And all other solutions can be constructed by adding together appropriate multiples of these two solutions. This will give us that these two solutions can span the entire set of solutions. So now here the scientist is dealing with the homogeneous system of equations. So these two solutions which are linearly independent and which can span the entire set. So these two solutions form a basis for null A. So I can say that dimension of null A is 2. Since there are only two vectors in the basis of null space A. So dimension of null space A is 2. And here n is 42, and we know from the rank theorem that rank A plus dimension of null A is equal to n. So dimension of column space A is equal to rank A, that is 40. 42 minus 2, 40. So this will give us column space A has 40 vectors. The dimension of column space A is 40. That means column space A, the basis for column space A has 40 vectors. And column space A is a subspace of R40. Since the number of rows are 40, since the number of rows are 40, there will be 40 entries in each vector in column space A. So it is a subspace of R40 and its dimension also 40. So a subspace of R40 has 40 linearly independent sets, 40 linearly independent vectors. That means it is nothing but R40 R itself. So column space A is R40. So every non-homogeneous equation Ax is equal to B has a solution. When the column space A spans entire set, so every non-homogeneous system of the given system of 40 equations, even if we alter the zeros with some other non-zero elements, the system has a solution. So this is a beautiful example given in the book. And similarly, we can construct many more examples by simply by using this rank theorem. We can tell whether the solution exists or not. So with this, I am concluding today's class. Thank you for watching.